It's pretty exciting to welcome you all to our second research exchange, this time on the topic of colloidal gold transport in gold deposits. I think colloidal gold really has the potential to upturn the way we think about sort of how gold gets into very high grade deposits, and especially from an exploration point of view, how it might get trapped, or what might trigger its deposition. It could be very different to aqueous gold transport in aqueous complexes. So to start us off, we have Laura Petrella from the University of Western Australia. Laura graduated with a PhD from the University of Western Australia in 2019, and before that spent 3 years working as an exploration geologist in Australia. For a PhD, she applied a multidisciplinary and multi-scale approach to study the formation of high-grade gold deposits, high-grade gold mineralization at the world-class Cali gold deposit in Australia, and is currently a research associate at the Center for Exploration Targeting at UWA, where her research focuses on gold transport and deposition mechanisms associated with high-grade orogenic gold deposits. So Laura, you're already sharing your screen.
Yep.
I'll hand over to you.
Thank you, Tom. Hi, everyone. Thanks for coming along. So today I will be talking about colloidal gold in orogenic gold deposits. But before I start, I would like to acknowledge my co-authors here at the University of Western Australia and at Curtin University and Newmont, as this project is very much of a team effort. So we will talk about colloids. So I will briefly review what they are. So when we talk about gold colloid, we refer to a solid particle that is entirely made of gold atoms and that is of nanometric size. To be called a colloid, this nanoparticle must be dispersed and in a stable suspension in a different medium. And in our case, this medium would be a hydrothermal solution. So the gold colloids are negatively charged. They have a large surface area compared to their volume, which gives them unique properties. And they nucleate or they form from a hydrothermal solution that is supersaturated in gold. And we are so interested in gold colloids because they allow for the concentration of 5,000 times more gold in solution than aqueous species. And that's something that is quite important to consider when you're studying gold mineralization. So because gold colloids are negatively charged, they tend to mutually repulse each other. However, the repulsive forces between them can easily be overcome, and that would occur, for example, when you have an increased collision rates between the particles. And we consider that at the temperature of formation of most orogenic gold deposit, the gold colloids will coagulate spontaneously. However, this spontaneous aggregation of gold colloids can be overcome if they're protected by colloidal silica. But that is something that Weihua will talk about shortly, as he conducted experiments on this. The idea of the contribution of gold colloid to formation of mineralization is not new. It has been proposed approximately 100 years ago to explain bonanza grade in epithermal deposits. But for orogenic gold mineralization, it's a bit more recent that Harrington and Wilkinson proposed that silica and gold colloids could be responsible for the formation of mineralization in these systems. And it is only very recently, in the last couple of years, that we have been able to image a gold nanoparticle in orogenic deposits. And that is thanks to the easier access to technologies such as transmission electron microscopy, or TEM, that allows for the imaging of very small objects. This slide is to really briefly review what is orogenic mineralization. And so these mineralized systems are gold only. They form in metamorphic belts, and the mineralization is structurally controlled. They are placed at mid-crustal depth, so they formed at temperature between 250 and 400 degrees Celsius, and the pressure range from 500 to 1,500 bars approximately. Their mineralizing fluid is characterized by low salinity. They're generally rich in carbon and H2S, and their pH is near neutral. One of the characteristics of orogenic gold mineralization is that it can produce extremely rich gold veins. And this is an example from the Red Lake mine in Canada, where you see this relatively narrow vein that is highly concentrated in gold. And to form this type of mineralization that is highly localized and very, very high grade, it is difficult to explain with a gold transport as an aqueous species, because these species have limited solubility or maximum concentration in hydrothermal solution. And because evidences for the contribution of gold colloid to orogenic deposits are rare, their contribution to the formation of mineralization was considered not very significant. So with this study, what we wanted to do is investigate how commonly gold colloid would occur in orogenic system and try to gain as much information on them as possible. So what we did is selected samples from 5 high-grade orogenic deposits that were formed at different ages, different depths, and in different host rock. And we looked at them using a transmission electron microscopy and tried to find evidence for colloidal gold. So these are the 5 samples that we used. So they are from different mines from different parts of the world. 3 of these mine deposits were formed in the Archean. 1 was formed in the Paleoproterozoic and 1 in the Cretaceous. They also formed at different depths. And all of these samples are quartz veins that are very rich in gold. This is the method that we used. So I used the example of our Red Lake sample. We made a month out of this sample, and we looked at it with the SEM. At this stage, what we did is targeting inclusion in the gold. So the light gray that you see on this backscatter image is a gold grain. And some of these dark spots in the gold are inclusion. So we selected interested inclusion that we extracted to look at with the TEM. So this is how we extract this very small sample that we call a foil. And so you can see that this foil is actually coming from this sample. So the bright spot that you see here is the inclusion we targeted here. And it is all surrounded by gold. This is TEM image from the same sample I just showed previously. This is a zoom on the inclusion, and that is the area we are interested in. So you can see that this inclusion is filled with amorphous material. There's no atomic arrangement in this phase, so it is definitely amorphous, and it contains several nanoparticles that are easily seen here. This is an element map of the inclusion, and you can see that the amorphous material is made of carbon, and the nanoparticles are made of silver and gold. These 2 images here are high-resolution TEM images and of some of the nanoparticles. So this nanoparticle size varies between 2 nanometer to 20 nanometer. And hopefully you might see on your screen some dark lines. So these lines are lines of atoms, and we are able to measure the distances between the atoms, and that confirmed, and the distance between them confirmed that these nanoparticles are indeed made of electron. And so I don't have time to show you all of my data, so you will have to trust me when I say that we did find nanoparticles in all our samples. We found nanoparticles of electrum or gold or silver oxide or even copper. Usually the nanoparticles are within amorphous carbon or amorphous silica or both, or in one case they are in a macrocrystalline carbon inclusion. We have been able to analyze the amorphous carbon phase, and it is obviously mostly composed of carbon, but also contains a significant amount of oxygen and nitrogen. And that is an important or interesting observation because this is a composition that approaches the carbonic-rich fluid inclusion in orogenic deposits. These carbonic-rich fluid inclusion are usually composed of CO2, or CH4, and N2. In terms of implication of our study, so this work is still in progress, but so far we think that our data set clearly points towards a genetic association between metal nanoparticles and amorphous silica and carbon. We think that a silica gel containing colloids was deposited in the veins together with amorphous carbon prior to the crystallization of gold. When gold crystallized, some of this amorphous material got trapped as inclusions, and that's what allowed for the preservation of the nanoparticle textures. Now, something that would be very interesting to discuss is where did these colloids nucleated? Did they nucleate at the sites of deposition? So they nucleated and they straight away aggregated and formed mineralization. Or the second option would be that they nucleated at depth and they have been transported until they reached the site of mineralization where they aggregated. And so this transport through the crust might have been possible if they had been associated with colloidal silica. In conclusion, our study clearly shows that metal colloids are not rare. It's quite the opposite. They're quite common in orogenic deposits. So that tells us that processes associated with nucleation or aggregation of metal colloids are quite important to understand the formation of gold mineralization. We also show an association between metal nanoparticles and amorphous silica and carbon, and that can help us to try to understand better the behavior of these colloids. But we will also require more experimental work on this. And because we still have so many questions regarding gold colloids, I'm very excited to say that we will start soon a new research project that is entitled Defining the Multi-Scale Controls on High-Grade Mineralization within Gold Deposits. So this project will be done with an amazing team across different institutions. We are supported by 3 industry sponsored and funded by the Australian Research Council. So our project will be a 3-year project where we will combine observation from natural system with experimental work and try to understand better the behavior of colloids. And that's it for my presentation. Thank you very much for listening to me.
Excellent. Thanks, Laura.
Thank you very much for your talk, Laura, and I'm looking forward to the next one. So Gülcan Bozkaya is a professor of economic geology at the Pamukkale University in Denizli, where she's been since 2012. Her interests are in the genesis of hydrothermal ore deposits, the pressure, temperature, and chemistry and source of all fluids, and applications of fluid inclusion studies. Gülcan currently directs the Pamukkale University Fluid Inclusion Laboratory, and her current research focuses on the formation of porphyry to epithermal type deposits, in particular gold deposits, and the evolution of active geothermal systems. So with that, I'd like to pass it over to you, Gülcan, and really look forward to your talk.
Okay, thank you, Alannah, for introduction, and thanks to Ore Deposit Hub team for kind invitation. When we think of transporting elements to make deposit, it is solubility in solution we should consider. For most elements, solubility as Clore complexes, but in Clore complexes is important, but gold is different being complexes, primary as bisulfide. These are sensitive to change in pressure, breaking down to hydrogen bisulfide and depositing gold. The atoms aggregate forming nanoparticles, colloids, and depositing, and eventually macroscopic crystals. In our study, we present evidence that gold colloids are present in mineralizing fluids and provide concentrations greater than possible in solution. Colloidal gold features and transport have been postulated for many years, first by Lindgren in 1950 and 1933, but more recently mainly by Jim Sanders and Harrington Wilkinson, believe that ore features can be attributed to colloidal gold, but no evidence of colloids in fluids or colloids in ores. Huff and Rai have shown the presence of gold nanoparticles in the superficial environment and shown the association with bacteria. Hennington and his team recently reported cold colloids in the filtrates from the black smokers. it was the gold-rich bands that are present in many of the United States epithermal deposits that gave the idea of colloidal transport rather than direct precipitation from solution. Extremely gold-rich band, as you can see, form at a variety of scales. And in the bottom two images, you can see the aggregation of the sub-micron colloidal particles, which are part of the way to forming the larger layers. What is not clear is whether the particles were transported at this scale or have formed from smaller ones. In this diagram from Hauf et al., they summarize the different environments and process for gold in the supergene and hypogene environment. In this presentation, we are only concerned with gold forming from the hydrothermal fluids, and gold is often found in small fractures and in pyrite of oxidized pyrite crystals. An example of that is shown here from the PhD of Matt Grimshaw at Leeds, where gold is associated with pyrite. The reflected light image on the right shows gold as masses in pyrite and along small fractures. However, the electron backscatter diffraction image you can see on the left reveals the crystal structure of the gold. Different crystal orientation and the presence of twin and grain boundaries here you can see are revealed. So this is the endpoint when macroscopic gold has been formed from the nanoparticle or colloidal suspensions. We can see in this slide scanning electron microscope images from Sardis, Turkey, where large crystalline gold has been formed from nanoparticles. The larger 10 to 100 nanometer clumps are made from the individual 10 nanometer crystals. So in the top of the right image, we see the smooth feature, which is a bacteria coated with gold nanoparticles, and in some instances, the bacteria act to precipitate the nanoparticles. The image on the left shows layers of layers of about 100 nanometer nanoparticle, which is in the middle left are bent and deformed, but in the bottom left, they are recrystallizing to form crystalline gold, not the angle of the layers forming crystal structures. The bottom middle shows new crystalline gold. Here, the lower crystal has a darker zone due to less gold in the structure. The bottom right image shows nanoparticles having formed plate-like layers, which have spherical. The bottom right image shows the nanoparticles having formed plate-like layers, which have spherical nanoparticles aggregates precipitated on top of them. Is that okay right now? Okay. There are numerous deposits in the Biga Peninsula, northern western Turkey, as you can see here from low to high sulfidation. They are mainly gold dominated or base metal with gold. All of them has a low salinity fluid. Samples come from Arap-Chandere intermediate sulfidation epithermal deposits here, and mainly base metal and minor gold minor. So image on right shows completely section of Ödral quartz as double polished fluid inclusion wafer. Left one here illuminated by white light from above with areas of dense accumulation of fluid inclusions appearing as white liner features. Right one is the SEM cathode luminance montage showing growth zones and different fluids pulses that precipitation. Here the fluid inclusion can be seen as a black dark liner features. Image on left in the composite and individual element map of the large inclusions that contain numerous small solids. Here you can see the different colors represent different main elements. We see the coating in the flute inclusions are dominated by calcium and sulfur. These are the images of the large flute inclusions that have been opened during polishing of the quartz wafer. The majority of the contents will have been lost, but we can still some gold particles attached to the inclusion wall. The particles are always rounded, as you can see here, and brightest solid due to their high atomic number. Here is the backscattered element map of one of the largest particle, about 1 micrometer. The element maps, we can see the gold, silver, copper, and the mercury is present. So these are effectively particles of a gold alloy. In high magnification image of the interior of the open inclusions, we can see numerous smaller than 1 micrometer particles attached to the coating of calcite in inclusions. There are other minerals also present, but gold is always rounded and the brightest phase. There are obviously a large number of these particles in the inclusions. In the flute inclusions from Arapçandere deposit, the gold particles were reasonably large colloidal particles. In these flute inclusions from the Kola borehole, the gold particles are true nanoparticles, much smaller, and are dispersed throughout the flute inclusions. The inclusions are illuminated shining a red laser at angle of the flute inclusions and observing the reflected light. In inclusions without nanoparticles, there is no reflection from the solution. The only reflection comes at interface, quartz flute inclusion and fluid vapor bubble. In the other images, we see bright red reflection from the fluid and intense white reflection from the vapor bubble, where there is a higher accumulation of particles, like throughout flutation. Here you can see the salt cube shows no reflection. You can also note that in these inclusions in transmitted light, the vapor bubble appears almost completely black due to skin of nanoparticles preventing the transmitted light. We analyzed the flute inclusions with laser ablation ICP-MS. Here we show the ablation profiles. All contains gold, silver, and these are only recorded when the sodium-potassium peaks from flute inclusion solution are present. There is no gold or silver in the quartz, as you can see here, but we continue to ablate. So noticeable feature is the gold and silver signal is spiky here, indicating particles in contrast to sodium and potassium, which is smooth asymmetric. Gold and silver pairs presented show a range of silver ratio, which is common in epithermal and other type of gold, other types of gold. Average values are about 50 ppm for gold and 35 ppm for silver. But values go much higher to 100 ppm, and some gold only signals can reach about 1000 ppm gold. These values can be considered as minimum values because the ICP-MS measures these particles precipitated because the ICP-MS measures elements sequentially, and therefore some particles would be missed when the mass spectrometer was measuring another element. Because there is order to magnitude difference in the concentration, it is unlikely these particles precipitated from solution when they were trapped as flute inclusions. The variability is due to heterogeneous trapping of the particles and the issues of measuring. So they were transported as particles. So we have shown both visually and analytical the presence of gold and silver particles in flute inclusions. We suggest These were precipitated deeper in the system and transport in magmatic vapors and trapped between gold fibers in the overgrowths. So concentration gold are very high, and we have confirmed with time flight mass spectrometer as well as bulk of the analysis by quadruple. We have mechanism of transporting large amounts of gold much more than possible in solution. So the figure shows the possibility of how much gold can be transported in solution. Clearly, this is lower than we have recorded when there are particles present. This has obvious implications for the amount of fluid that is needed to transport gold and make deposits. Thank you.
Excellent. Thanks, Gülcan. That was good. Okay, we'll go straight on to Weihua's talk. Great. Okay, so for the experimental perspective, we have Weihua Liu from CSIRO. Weihua obtained his PhD degree in geochemistry at Monash University in 2003. And since then, he has worked as a postdoctoral fellow, then a research scientist, and a senior scientist at CSIRO Minerals. He conducts experimental and theoretical studies to investigate mineral solubility, metal speciation, and fluid mineral reactions in hydrothermal fluids relevant to ore formation and mineral processing systems. So, Weihua, over to you.
Thanks, Tom and Alannah for giving me the chance to talk our research. I'll be talking some experimental evidence of gold nanoparticles in sulphur-bearing hydrothermal or fluids to see if the study can support what Laura and Gülcan have found in real ore gold deposit. This is a teamwork, my colleague within CSIRO and collaborators at Monash University and the Australian synchrotron. So to the breaking news, that's in 2018, this is made to ABC News in Australia. Laura has done the research actually from this mine. I just found from her slide. So it's really incredible, especially when you see this beautiful gold with quartz, this intimate relationship. And really, one would wonder how this form, how can that be formed from aqueous complex like ppb to 1 ppm level. And the recent evidence, in addition to what Laura and Gülcan just has mentioned, there are lots of new evidence due to the advance of the modern macroanalysis technique. So like Sanders, there's a long-term colloid researcher, got beautiful nanoparticles in epithermal ores, and also modern seafloor black smoker fluids like by Huntington's group and Gartman. And also Willie Jones gave a talk in 2019, showed a beautiful picture of this Bruce Jack epithermal gold silver deposit in Canada. I can't find the image on the web here, but and the latest one, just 3 months, 4 months ago, there's a study by Prokofiev et al. In scientific report reporting exceptional high concentration of gold in fluid inclusion from the deepest borehole in the earth. So evidence are mounting, and we try to look at from the experimental or theoretical background point of view. For key question for experimentalists like me is can we mimic or make gold nanoparticles in hydrothermal fluid in the lab that are similar to ore fluids? And there is a pioneer study, both speakers mentioned, in that more than 80 years ago by Frondo. He used potassium carbonate and hydrogen peroxide that make a reducing condition is very weird. And no sulfur, but they found colloid gold is stable in hydrothermal fluid, especially supported by colloidal silica. And here we want to report the gold colloids in sulphur-bearing ore fluid because sulfur is intimate relationship with gold, especially aqueous gold complex. So gold hydrosulfide complex is almost the most important gold complexing agent. So first step, we're making gold in the laboratory. I quickly show you how do we make it. We just go through 3 solution and we drop sodium bisulfide dilute solution, and you can see at 70 to 90 degrees in half an hour, it will become beautiful red wine color, and it will be stable for a couple of days. But if we put colloidal silica, and then stability of those gold colloid at room temperature is increased, and we can pH is down to around 4. Below 4 is destabilized. Note that the bottom, this black is the mark by panes, not precipitates. And then before we heat this colloidal solution, we did TEM images, and you can see that without colloidal silica, just gold nanoparticles in classic citrate-based solutions. So you can see nice, that's a very classical shape of gold nanoparticles. And with sodium bisulfide-based solution, we can also see them. And if we put colloidal silica, you can see the light gray color are colloidal silica particles. And those images are taken TEM, it's a natural evaporating of the gold colloidal solution, so it's already air dried. And then we take the solution to a next door Australian synchrotron at their XAS, X-ray absorption spectroscopy beamline, and use a little device called a hot air gun, very simple one, to heat, put the sample in the capillary tube and heat to just up to 225 C and measure the spectrum. And before we do anything, we need to know the gold is in solution on the right-hand side, not in the precipitate on the wall. So we scan the sample cell across, and we can see if it's noisy, like this one is a gold precipitate. But if it's really smooth transition, that means gold is a homogenized distribute in the solution. So look here, at 25 is very clean, but 150 without colloidal silica is already precipitate. But with the colloidal silica, the 225 is still really nicely stay in the solution. And then we measure X-ray near edge spectroscopy, which can tell local structure of gold. And this is standard spectra of gold zero, gold metal, and this is gold aqueous solution of gold chloride. You can see our sample spectra exactly look like gold metal spectra. All the measurements are like that, as long as it stays in the solution. So gold nanoparticles are stable up to 225 and the pH 4 to 10, but when supported by colloidal silica. We didn't do higher temperature experiment there because we haven't, since then we got beam time, we got an experimental device, but couldn't run it last 2 years, almost after lockdown. And then we also did some room temperature just by visual check, because the gold nanoparticle solution is nicely colored. So we just heat up in the laboratory oven and look at the color change. So without colloidal silica, any citrate-based solution, just up to 250, 260, just all aggregates, precipitate. And when sodium bisulfide solution supported by colloidal silica, up to 300 C is almost there. 350, you can see it's already started aggregation. And after the heating, we took the sample to do the TEM again, and we can see the 300 C heated samples, gold colloids are almost still in the solution. but it slowly start to aggregate a little bit. But 350, both colloidal silica and gold colloid, they all start aggregate this nice Oswald ripening features that to joined to one. This feature very clear. So our funding is up to 300 C, like looks like it can be stable, but above that it start to precipitate. And the solution we use is around 100 ppm. If we will go higher, it's getting a bit worse. But just a few months ago, this Proclif, their paper, they found 750 ppm in the fluid inclusion of this Archean gold mineralization in the Kola super deep borehole in northwest Russia, and this is really, really high. So how to form those gold colloid in the solution? It's basically the same process of reducing gold 1+ in the solution to gold 0. So the boiling is the most effective way to concentrate gold. Is almost all previous studies from Sanders, Huntington, and Willie Jones group, they all agree that boiling is the most effective way to concentrate gold to gold nanoparticles. And also, if we find some metal sulfide, that also will remove the hydrosulfide ligand and promote the formation of the gold 0. But that was straight form to the solid gold. So we need some capping agent, like traditional citrate. We find sulfide as well. And in literature, there's a chemical engineering literature. They use carbon monoxide, carbonate, salts, ammonia, organic function groups, heaps of ligands to stabilize gold nanoparticle at room temperature. So at high temperature in geological fluid, we really don't know what all this play in how this play in the role to stabilize gold nanoparticles. And it's obvious from 1938 from the study and our study that colloidal silica really support gold nanoparticles at high temperature. So how to destabilize the thing? If we keep boiling, it over-concentrated, so it will gold will precipitate, and also fluid mixing and adding salt, because that will increase ionic strength, that too much charge, gold nanoparticle also cannot stay in the solution. The key thing is gold particles is supported by electric double layer, and anything destroy this double layer will cause gold or precipitate. So this is just a quick cook and look study, but the takeaway message is very clear. We think it's when supported by colloidal silica, gold nanoparticle can be stable in sulphur-bearing fluids, and this is probably a very effective way to concentrate gold in hydrothermal sulphur-bearing fluids to form high-grade gold ores. And we're glad that Laura and colleagues, the collaborators, are taking a new study funded by RC to do further this line of work. So very exciting. So just acknowledge some funding agencies, and thanks for watching and listening.
Great. Thanks a lot, Weihua. That was incredibly interesting. And really, it's exciting to see what research can be done on those crucial capping agents. They seem like they would vary between the deposit types, right?
Yeah.
All right. So now we'll move on to the discussion, and we kind of want this to be, a bit more sort of discursive and constructive, maybe, than our typical Q&A, grilling the speakers. So, I mean, for starters, do the speakers, you can all unmute yourselves as you need if you have any questions for each other. And then me and Alannah will feed questions in from the chat, sort of, if it makes sense. And there's a little instruction in the chat there for how to ask those questions if you want to ask it yourself. Or anonymously. Great.
Can I ask a question to Weihua?
Mm-hmm.
Weihua, what do you think will happen above 300 degrees? Is there any way to prevent aggregation of gold colloids?
Yes, maybe, but in the simple system we tried, it starts aggregating. But if the solution composition is different from our experimental solution, which is a very simple sodium bisulfite solution, and the capping agent is different. So if you got a different capping agent, like some weird carbon species in your, you mentioned a very close relationship with the carbon. I really just don't know. Yeah, must be a way to make it stable.
We need to look into this.
One thing that, I mean, Laura, you posed that question at the end, and a thing that kept coming to mind with both of the deposit types, and just every time I hear gold talks, is at some point you need to raise concentrations above that you can reach with aqueous species. You need to remove fluid from the particles, right? You need like some kind of natural sieve, you know, very broadly speaking. Where could you envision, I guess it was the open question, but where could we envision that happening, and what might it look like geologically? The place where we concentrate particles and remove water. Mark Hannington, like they described some convincing systems in black smoker systems, but these are very different.
Of course, the most obvious location for the nucleation of nanoparticle would be the site of mineralization, because that's where you have a fracture change, rapid change of pressure, so changes to the fluid composition or to the fluid pressure. However, if we nucleate nanoparticle at the site of deposition, that doesn't solve our problem of the low solubility of aqueous species. In the that we would need really a lot of fluid to go through these tiny veins. That is still something that we cannot explain. So we are thinking of maybe it is possible to nucleate nanoparticles a bit further down the crust, probably deeper than the site of mineralization, but that's unclear which process would be responsible for the nucleation of nanoparticles.
Do you have a perspective?
In the aseismic refinement concept.
So the aseismic refinement concept is what was proposed by Chris Voisey. So this concept is, the way I understand it, is more of a remobilization of gold. So in Chris's model, the gold is already deposited in the vein, and the aseismic refinement is the way that you remobilize this gold as nanoparticle inside the quartz veins. I'm not exactly sure if I'm answering this question, but this model doesn't answer the question of how you transported that much gold in the vein in the first place. So we still face the same issue of mass balance issue, I would say.
Yeah, thanks for explaining that. I hope that helps, Manuel. Tom, another question. Do you want to? There's a couple more in the chat there, where I can.
One from Annika Vostrom. The question is: are any primary nanoparticle structures preserved in greenschist amphibolite facies, or are all destroyed? I guess that really applies to, maybe mostly applies to the orogenic domain, but could apply to anything. I guess just general preservation.
So they are, They are preserved. That's how we've been able to image them. So they are preserved, I think, because well, we found them only in micro inclusion in gold. So we think that the gold surrounding the inclusion preserved what's inside. So the amorphous state of carbon or silica, and that's what allowed the preservation of the nanoparticle trapped inside. And we have nanoparticle preserved from the Archean. So they can be, yeah, they can be preserved.
Actually, I have a question. From your presentation, if the silica needed to stabilize nanoparticles, why when gold fills cracks in pyrite, etc., is there no silica with gold?
Well, in some cases, we're not sure this gold in the microfractures of pyrite or arsenopyrite, we're not sure the colloidal gold in the first place. Some of this gold might have been inside the sulfide structure in the first place. So I'm not sure it is the same type of colloidal gold in this case.
Someone asked about the temperatures that Weihua saw in his experiments, and if those temperatures would be common in epithermal deposits and therefore have more common colloidal gold in that system. Or maybe you can comment in general about the temperature differences in orogenic versus epithermal, and if that would cause some difference in the abundance of colloidal gold.
I'm sorry. In epithermal system, actually related with all the particles being trapped by quartz in epithermal system. For example, in Arap Chandere, I showed in my talk, as
difference between epithermal and orogenic gold is in epithermal system, boiling is much more observed. Yeah. So probably that's the reason. Lots of the earlier study on nanoparticle gold deposit is or most of them are epithermal. But with the LoRa study and with this Russian deep, super deep borehole study, that can really probably different mechanism is causing the stabilized gold nanoparticles in higher temperature and pressure, and it's not boiling. So there's some fundamental deep cause to this difference between epithermal and the gold and the orogenic, but we don't know. I don't know.
Oh, that's right. We can mainly, the boiling is very important for the epithermal system. You're right.
In orogenic system, you have a phase separation that can also be processed similar to boiling. That would be induced by a reaction of the fluid with a really reductive host rock or rapid pressure change. However, we're unsure if these mechanisms are associated with the aggregation of the nanoparticle. We don't know yet.
Okay, so something's still up for investigation further.
A lot.
Yeah.
Okay, we have an interesting question here from Bjorn van der Heyden. Bjorn, do you want to ask it yourself?
Thank you, Tom, and thank you to all the speakers for talks. Laura, my question was directed to you. I just sort of followed your arguments about the amorphous carbon having a similar sort of chemical signature to the supercritical fluid that we would expect in an orogenic system, right? So that, to me, that tells me that that amorphous carbon probably then precipitated on the exhumation pathway sometime between, we had formed at 20 kilometers depth and surface where you collected your samples. So can that same sort of process be happening to the gold? And could it be that you got a supersaturated solution at depth and then these nanoparticles then form only on that exhumation pathway? How do you discount that?
Well, we don't discount it. They have to be formed from a supersaturated solution anyway. We just don't know at which stage it happened. So nothing is discounted. I'm sorry, I can't answer this question because I just don't know.
I have one quick question.
Yep.
Thanks for all presentations. I have a quick question to Dr. Liu. It's out of our focus topic, but just I wonder, because the presentation was really interesting, and I wonder about the, can we use all this background for the ore dressing procedure, because we are looking to gold's behavior in this conditions, colloidal conditions, and how can we apply all these procedures to ore dressing or mineral extraction? Did you ever think about it, or this information can give us some ideas about it? I just wonder and want to learn from you. Thank you.
Thank you for the question. I really haven't thought about how can we use this for the mineral processing, because nanoparticle is really is a one-way irreversible one-way traffic to nuclear nanoparticles, then aggregates as solid gold. So if we want to get this solid gold out of ores, I'm not sure if it has to go to nanoparticle stage. Probably not.
I see.
Yeah, but I really haven't thought hard.
I just if I think reverse, maybe we can apply this kind of studies to ore dressing, and it could be useful for mining engineers. What to share it with you. Thank you.
Yeah, interesting suggestion. Thanks, Somer. Alannah, have you got one there, or any of the speakers? If something's growing on your mind?
Maybe just a quick one here, also from Gülcan. For all the speakers, has there been colloidal type, or these type of process nanoparticles in other base metal sulfide systems, not just gold? I think Lara, you mentioned copper. You also found nanoparticles copper, maybe? If anyone has other input there.
Yeah, thanks, Alannah. Just to sort of clarify that question
a
little
sorry.
bit further. No, hundreds. Thank you so much. I wanted to know how universal this sort of process might be across other ore systems as well, not because I haven't done much reading about it. I thought maybe you guys who've been doing a lot of research in the area might have seen stuff from sort of interdisciplinary type research or studies that show this in, I don't know, base metal sulfides, just as an example.
Yeah. Should we start with Laura and work our way down?
Actually, I don't think there has been much research on the potential metal transport of another form of colloid in other systems. So I don't think there is actually, but I might be wrong.
Let's see, Weihua or Weihua next.
There's some zinc sulfide nanoparticles very popular research for this chloroform zinc ore for the Mississippi type ore deposit, but there's some controversy there. Some people think there's gold zinc sulfide nanoparticles formation, but most people don't think so. They're still debating.
Sorry, just to follow on there, we are. Why don't they think it's a process there, and the arguments against it, would they be applicable here as well?
All right, Gülcan, you have anything to add there? Any other metals or deposit types?
Yes, any other metal nanoparticles being found, if I'm not wrong. Yeah, not just the gold, but.
See, there's also a comment in the chat there that tin cassiterite shows similarities. Oh, in structurally controlled settings. I'm not sure if that's colloidal or not, but maybe it is. Should we do one last question, Tom, or?
May I raise? Yeah, just quick question, please.
Yeah, go for it.
Yeah, thank you very much for the excellent speeches given by three of the talkers. I was wondering if the silica is deposited in the form of colloids, or we have the colloidal silica deposits. Does it imply that the gold is also deposited in the form, or there is another mechanism that gold also deposits? I mean we see the colloidal silica deposition in the epithermal systems, does it imply that gold is also deposited in that form, or it may be deposited or carried in other, like ionic forms or some other forms as well? Thank you.
Yeah, I guess that's probably for Gülcan.
Yeah, I mean the silica form very common related with the colloidal, not just colloidal, but gold deposits, epithermal gold deposits is very common, if I got your questions correct.
Yeah.
I wonder if you can say that strictly, when we see the colloidal silica deposition, gold also has to be deposited in the same form.
But in the silica systems, the gold is as nanoparticles, not ionic structure.
Yeah, I suppose there's also lots of cases where there's colloidal silica and no gold whatsoever.
Yeah, if it is
outside of ore deposits. Yeah.
Yeah.
All right. Thanks, Ekati. So maybe got another question here from Laren Diamond. Laren, do you want to unmute yourself?
Sure. Thanks very much for the talks. I have a question for Weihua. You mentioned that let's say the destruction of nanoparticulate gold, or the precipitation of it anyway, is a one-way process. And so I'm wondering if that's true, how to actually form the nanoparticles in the first place. Do you think it could be reflecting leaching of gold in the source rock? The gold is already present as nanoparticles, and it's just being transported, mobilized in that state to begin with. Or how do we generate those nanoparticles in the source rock?
I think it's very high temperature pressure. As the aqueous complex, gold has a very high solubility with high temperature pressure. So those fluids can, very attacking fluids can dissolve gold from the source rock as the aqueous complex. When temperature and pressure change and the other water rock interaction, then like boiling, then those aqueous complex be destabilized and then will form nanoparticles as intermediate stage of form solid gold eventually. So now only the question is how long is this nanoparticle stage? Is it long enough to long distance, long time, long lifespan transport, or is a quick, very short lifespan, just the intermediate stage of a precipitate? But they're all, at this stage, they all should be from aqueous fluid, lower concentrated gold fluid, but continuous boiling, and that can concentrate gold nanoparticles. That's the most studied hypothesis.
Okay.
That way.
Thanks very much for your insight, Weihua. Thank you.
Thank you.
All right, then we're pretty much, we're a little bit over. I just wondered if all the speakers, if you have any sort of concluding remarks, maybe something you've learned or something some kind of outlook of what you might look into next, maybe starting from Laura and working through the list.
We definitely have so many questions left unanswered. That would be actually my work in the next 3 years, hopefully trying to address some of these questions. So I really look forward to this.
Okay. Gülcan?
So as I mentioned in my talk, I mean, we found the colloidal golds in one of the epithermal system from the northwestern Turkey. But as I showed in my talk, there are numerous deposits related with that. So there is still much to do related with them. I'm quite sure there are many deposits which contains colloidal gold, as we shown in our talks, as a colloidal, not inclusion as a solution.
Thanks. And Weihua, final remarks.
Thank you. Yeah, we found this gold colloid or nanoparticle things have changed or make challenges to our traditional way of doing the modeling and understanding, because there's no framework to rely on to model those systems. Unlike aqueous species that we use Hexagon's 1969 framework, and for the last 50, 60, 80 years, it's very comfortable and just adding new species, trying to understand more things. But this is a brand new, and we really need those surface chemists or the different discipline people to tackle this problem. So it can establish a framework that can actually understand and model this colloidal system as a whole.
Yeah, it sounds tough.
Yeah, it's very hard. I find it is hard.
Yeah.
But up to Laura to take it. Challenge the next 3 years.
Hopefully fruitful. I think for me, really interested in looking at these sort of continua between Kola deep borehole type sampling or source rock type sampling and orogenic gold deposits and porphyry deposits and epithermal deposits. You know, I reckon can pinpoint where these particles form and how they get transported. Okay. So with that, I think we'll end the meeting. Thank you very much to all the speakers and all the questions.
Yes, thank you.
Thank you. Thank you, Alannah and Tom.
Okay, take care. Have a good evening and morning. Bye-bye.
Hi, everyone.
Bye.